So good morning. Welcome to lecture 4. Last time I guess we left at triple five's introduction and let's first focus on what are the typical triple five properties that we have. Like we have already seen 741 typical properties. So in 1972, there is a lot of need of the timers, and some person came out with the idea of building a timer using op-amp because anyways op-amp has this habit of going into the saturation because of its high gain, and why not find a way to put it into a plus V set or minus V set based on the timing using capacitor. So remember, capacitor charging time is the only dynamic thing that we have over here, and because this is not stable over the time, we can achieve a timer. So no timer can be made without active elements, which are capacitors and inductors. Capacitors slowly charge for the voltage. At the same time, inductor slowly allows the flow of current through it. So that's why it acts as a high resistance initially, and as the time progresses, like this time is very small, maybe few microseconds also, but it's dynamic in nature. Whereas your resistor will not show this kind of curves everywhere. So all these curves are voltage versus time, and we typically don't study them in BEE subjects or EEE subjects because this is kind of time domain response. But later on in many courses, we have studied about a dynamic system that varies with the time. So capacitor and inductor are the two elements which makes the timing possible into the electronics. So IC 555 is an integrated circuit which is used for the different applications like timer. One example of timer is your alarm clock. सुबह 8 बजे let's say alarm आपको ring कराना है. So you can build it using IC 555. Second application is pulse generation. Now pulse generation का example, you might know stepper motor runs on the pulses. So you can use IC 555 to rotate a stepper motor, or there are many applications where pulse can be used. For example, your LED flashing or your disco lights, and everywhere where there is a pulse needed, we can generate it using IC 555. Next very important application is oscillators. Now, typically these oscillators are only rectangular wave or square wave, and some applications we call it a triangular wave generator also. But we need a wave shaping circuits to generate a sinusoid out of IC 555 because IC 555's output is TTL compatible. When I say TTL, it means transistor transistor logic. That means the output can only be 5 volts or it can be 0 volts. Okay, remember this thing. So if somebody says I have applied a IC 555 with 8 volt supply, still its output is gonna be 5 volt only because it's TTL compatible. So there is a gate inside this IC. Then again it gets its name from three 5K resistors. So we will see the voltage division law. Basically, what happens when you connect two resistors in series and you try to measure a voltage across this point VO. So basically, as per Ohm's law, the voltage across this point is current flowing through this resistor R2 and then into resistance R. V is equal to IR. So I into R2. But what is the current flowing through a series network? It is always same. So same current I will be flowing here, and that's why if I call this point as VCC, my current I will be basically total resistance in series will be addition of the two resistance, so R1 plus R2, and then total current is voltage upon resistance, so that becomes my I value. And now if I substitute this I value over here, what I will get is VO equal to R2 upon R1 plus R2 into VCC. I guess this voltage division law is very clear to everyone. If not, please remember it is very important law and it is used everywhere in op-amp derivations as well as triple five derivations. And they generally don't even tell this is coming from voltage division law. They directly write these kind of equations and then people get confused. So if you directly try to study a op-amp based book, they will not explain this concept. So this is a voltage division law with two resistors. Now let's try and understand what will happen if I put three resistors of same values and what are the three voltages generated. So I have three resistors 5K, 5K and 5K. So all of them are having same value and this is my voltage VCC. So if I try to see what is the voltage at this point, now my R2 is combination of these two. So I can easily write it is 10K upon 15K into VCC. Same law, voltage division law. Now you will see this KK gets cancelled and this becomes 2 by 3 VCC. So remember the voltage at this point is 2 by 3 VCC and it is irrespective of the value of the resistance. It only needs all the three values to be same. Okay. Next thing is the voltage at this point. So if you recalculate, and I'm sure you can do it, the answer should be 1 by 3 VCC. Now this time the voltage across this point, so 5K into total resistance is still same, which is 15K, and that's why it comes 1 by 3 times VCC. So with respect to triple five, you will always remember these two levels, 2/3 of VCC and 1/3 of VCC. Why we will see soon when we go inside the IC triple five. But the name triple five comes from these three 5K resistors. Next is depending upon the manufacturer, the package may include 25 transistors inside, two diodes, and 15 resistors. A silicon chip is typically 8-pin DIP, and DIP stands for dual inline package. Okay, so these are the three terms which makes this DIP, and it's available in CMOS type. So if it is a CMOS logic still, the voltage levels are the same, and ICM. So it the first C tells us for the CMOS type. By default, the output is TTL logic, and there is some variant of triple five called 556, which is a dual timer, and instead of 8 pins, this one has a 14 pin. And then there is another IC. I guess it's overlaid by the window over here. So I just move it. 558, which is a quad timer. So these are the variations of 555, and that's why their names are like that. It doesn't mean they have 5K, 5K, and 8K inside. And this one doesn't mean that this has 5K, 5K, and 6K inside. But since they are derived from IC triple five, that's why these three packages are there, other than regular IC triple five. And remember, this number is 7555 for CMOS variant of the IC. Now, this is what the IC looks from the inside. Uh, IC has three 5K resistors. Then they have two op amps. Remember, these op amps are single powered. So your VCC is 5 volts or any other voltage that you apply at this pin. But your VEE or negative voltage terminal with the op amp is 0 volts. So we have till this point learned the op amp 741, which requires plus 15 volt from the top and minus 15 volts at the base. But triple five IC is a single supply IC, so it does not require two batteries, and you can just put a single battery to connect your triple five IC, and that's why your op amps VCC becomes higher voltage and VE is actually grounded. Uh, the main advantage of this being output will be only positive at all the times at the output pin. Next thing, the op amp's negative terminal goes at 2/3 of VCC. Okay. and this comparator's positive terminal goes at 1/3 of VCC. Okay. Now, this op-amp's output will go high only if positive terminal voltage increases the negative terminal voltage. Okay. So this op-amp will switch only when my voltage at threshold pin crosses 2/3 of VCC. So it becomes more than of 2/3 of VCC. This op-amp will go high. As soon as this op-amp will go high, there is a flip-flop which we are going to see soon. Flip-flop is a digital circuit to which when we click a voltage at reset pin, its output goes low, and when we give a voltage at its set pins, its output goes high. So that is what the name flip-flop. It can change between high and low, and this particular output is given to pin number 3. Practically, it is not given directly from this SR flip-flop. So if you see in many books, they have given a Q bar, then a NOT gate, and then its output pin. Reason being, as soon as you put a NOT gate, it will change the Q bar value to Q. At the same time, it will increase the current carrying capacity of the output pin. So directly from SR flip-flop, the output is not given directly. It is going through a NOT gate to increase the current carrying capacity of the output. Then next is, so what will happen if it crosses 2/3 of VCC, reset pin will go high. As soon as reset pin will go high, the Q will become low, or QR will become high. And what will happen to comparator 2? Now comparator 2 will go high only if its positive terminal voltage is greater than negative terminal voltage, and its positive terminal voltage at this point is 1/3 VCC. And that's why if the trigger pin voltage goes below, so this is above 2/3 of VCC and this is below 1/3 of VCC, then this comparator output will go high, and that will set the flip-flop, and at that time your Q will become high, Q bar will become low, and output will go high. Now there is one more thing called transistor T1. So this transistor turns on whenever your QR goes high, and otherwise it will go off because there is no biasing to this transistor. This transistor is actually acting like a switch. So what will happen if you turn on this transistor? The discharge pin will get grounded, and if you turn off this transistor, the discharge pin will not get grounded. So it is obvious that this discharge pin must be going to some capacitor. Otherwise, the name discharge doesn't make any sense. Okay. Then there is a ground pin here. Now reset pin will reset this flip-flop itself. And that's why whenever you reset the flip-flop, its output is gonna go low. And that's why pin number 4 is the reset pin. Now there is something called as control voltage, and I will try to explain that in a minute. Let me go back to the paint. So now my question is, what will happen if you have 3 resistors like this? Okay, R1, R2, and R3. Now when we say I apply VCC, I typically get 2/3 of VCC here, and then I will get 1/3 of VCC here. Okay, but now if I apply another battery over here, whose value is some V volts. Now what will happen? Because of these V volts, the voltage at this point will be exactly V volts, provided it is less than 2/3 of VCC. It will cause a loading effect to the 2/3 of VCC, and it will change the value at this point. Okay. Now, as soon as say you applied 3 volts and this point was, let's say, 10 volts. So 2/3 of VCC will be 6.6 volts. So whenever you connect a 3 volt in parallel with the 6 volt, again, none of the electrical engineering book tells you what happens when you connect 2 supplies together. But I guess in the first lecture, I have already told you, when you connect 2 supplies with same polarity, the output voltage is always the lower voltage. Reason being, loading will happen and a higher voltage supply gives current to this battery, and this becomes dangerous because battery is not prepared to accept any current. This will reverse the chemical reaction inside and may damage the battery or may discharge this battery eventually. So at the end of the day, whichever is the lower voltage will always survive, and it's not good thing to do. It might blast the battery also. So never connect two supplies in parallel. You can connect them in series, but not in parallel. So next thing is, if this becomes V volts, then the voltage at this point is not one third of VCC anymore. And since both resistors of 5K are there, एक्चुअली यहाँ पे क्या होगा, यहाँ पे सीधा वोल्टेज हाफ हो जाएगा, क्योंकि वोल्टेज डिवीजन लॉ से क्या कहता है हम लोग, if you connect two resistance of same value together, then output is always VCC by 2. So this is what voltage division law says. If both resistors are of same values, then here the output is always half VCC, and same thing will happen here. The output at this point is half the voltage applied to this pin, and that's why now if you want to set the above flip flop, your let me go back to the I guess I can clear all the writings from this slide. Okay. So when I say I apply some control voltage at this pin, when I apply some control voltage at this point, now this comparator can go high only if I cross this control voltage. Okay. So control voltage will say the output Q bar, okay, will go high if threshold voltage crosses the control voltage in a positive manner. So if control voltage is 3 volt, and if this threshold voltage becomes 3.1 volt, then this comparator output will go high. Now, why we are calling it as a comparator? Comparator just compares negative terminal voltage with positive terminal voltage. Op-amp goes high when positive terminal voltage is greater than negative terminal voltage, and op-amp's output goes low when the negative terminal voltage is higher than positive terminal voltage. So that's why it is comparing A and B voltages greater than, less than, or equal to. Now equal to is a case where op-amp has to be ideal. So if you apply A and B equal values to the comparator, the output of the comparator should be exactly 0 volts. Now that will only happen if you have positive and negative VCC and minus VE. If A is greater than B, then output is plus VCC, and if A is less than B, the output is minus VE. In such case, you will have output equal to 0. But if you have single powered op-amp, then this output is exactly V by 2 volts. So we are not going into the details because this is the ideal case, will never happen. You are trying to compare A and B, and in any given circumstances A cannot be equal to B. इसमें कुछ तो noise आ जाएगा, इसमें कुछ तो noise आएगा, and somehow you cannot have two voltage sources of same value. Even if you have same batteries manufactured by the same company in the same lot, you cannot have this kind of ideal situation anywhere. Plus your op-amp is not ideal, so it will have its own offset current, and that's why you will never get this particular condition. So at that time, the trigger voltage will be control voltage by 2. And if you want to turn on the comparator 2, your trigger voltage pin should go below half the control voltage. So now your entire timing and operations are controlled by this control pin, and that's why the name control voltage. The only condition is control voltage should be less than 2/3 of VCC. If it is more, then your control voltage will not make any change in the output. So let me go to the next slide. So let's start one by one. The first thing in the op-amp circuit diagram is 3 5K resistors. I guess I have explained everything already, but let me just show it in the form of slides. So at this point, you will lose 1/3 of the voltage, and your output voltage is 2/3 of VCC. At this point, again, you will lose 1/3 of the VCC, and your output is 1/3 of VCC. Okay. And typically, if VCC is 5 volts, this is 2/3 of 5 volts, and this is 1/3 of 5 volts, which is, I guess, 3.3 volts and 1.67 volts. But you can check that. It's just maths. So yeah, I guess they have mentioned 3.3 volts over here and 1.65 volts over here. Next is we have comparator. So comparator, one comparator has 3.33. So this comparator output will go high if your input voltage, that is pin number 5, is 3.3 volts and above. Okay. So they have written 3.34, which is already greater than 3.3, and that's why they have put equal to sign. Similarly, I guess there is some mistake. This should be 1.66. And then if you want this comparator B output should go high, your input should be less than 1.66. Next is RS flip-flop. So RS flip-flop are typically a comparator, reset pin, set pin, and Q bar. So whenever reset pin goes high, Q bar goes high, and whenever set pin goes high, the output Q bar goes low. Then this particular pin is reset for the flip-flop itself. So whenever you apply a high voltage at this pin, this will reset the flip-flop, and the logic of NOT gate is there. So reset pin should not go low. So this NOT gate is actually converting your reset pin from logic 1 to logic 0. Let's say if I turn on something by giving a pulse, the bulb will glow. Okay. Now same thing if I put a NOT gate and same circuit is there. Now instead of giving a pulse high, I need to give pulse low. Because of this NOT gate, that pulse will get converted into high, and then that bulb will stop glowing. Same thing, this bubble whenever shown with the digital circuit, that means there is a NOT gate present, and instead of giving high to the reset pin, we need to give logic 0 to reset this particular flip-flop. Then there is a discharge capacitor connected to Q bar. So whenever this output goes low, the discharge capacitor basically opens up, and whenever this Q bar goes high, the discharge capacitor will become short and will allow passage of the current. Now this is the same block diagram drawn in a different way, and as I told you, the input is not taken, output is not taken from the Q. It is all actually given by the output buffer, which increases the current limit of the. Next is discharge capacitor. So whenever there is a voltage, there is a current. So this particular transistor, I don't know whether you have studied transistor in EEE, but transistor has something called as saturation mode, in which there is a plenty of electrons available in the transistor and your current can easily flow. And then there is a mode called cutoff mode, where there is no current flow and your transistor acts as an open circuit, and that's why the name transfer of resistor transistors. So basically it can offer a open circuit, which is a cutoff region, and it can offer a closed circuit or 0 ohms when in the saturation region. So transistor can change its resistance based on the type of the input you apply to the transistor, and that's why the name is also transistor. Next is output buffer. So output buffer is basically a NOT gate. That's why whenever there is a logic high here, your output goes low. And the simple way to connect this output, or simple reason to connect this output buffer, is to increase the current of the IC 555. So let's see what is there inside IC 555. We are learning this IC in detail because our next practical will be based on the timers. Most of you might have finished integrator and differentiator based on IC 741, and before that first week we have studied about digital gates. Now you will realize I am trying to bring the theory and practical together, so it might happen that sometime later I have to switch back to DLD where I left this topic in half. Then I started 741. Again, I have to left this topic in half because next week's experiment will be timers. Even today's batch, even will perform the timer experiment. That's why I'm teaching timer first. And I'm trying to bring everything in synchronization, which might hamper the lecture delivery in order. So if you are not getting any particular topic, this particular digital logic lecture can be seen after my first lecture, and you can offline connect everything in proper order to watch the lectures in sequence. But while delivering the lectures, I will try to deliver the theory just before the practical, so that in the practical you don't go blank. So this is a third way to draw the internal block diagram of IC 555. By this time, you might have realized there are two op amps, there are two 555K resistors, there is one flip flop, there is one driver, and there is one transistor. That's all you see in the block diagram. As per the pin goes, the first pin goes to the ground, the last pin goes to the VCC. Okay, pin 2 is trigger pin. Here we say it active low because when it goes, when the output is greater than 1/3 of VCC at this particular pin, that makes output high. So it monitors the discharging timing of the capacitor in an unstable circuit. So basically, pin 2 is associated with 1/3 of VCC. Then pin 3 is the actual output pin of the IC. It can drive any TTL circuits and capable of providing 200 milliampere. So remember, if you have motor of 160 milliampere, you can directly connect to IC 555 without any driver. And it is equal to roughly VCC can work from 1.5 volts also. So even if you have a small battery to power IC 555, you can use that. Now there is a internal circuit which will reduce your output level to corresponding logic 1. So 1.2 volts is also considered as logic 1 if the battery is 1.5 volt. Typically, I said you the limit is 2.2. Anything about 2.2 volt is always logic 1. But if your battery voltage is not 5 volts, and if you are applying either two batteries of 1.5 volt in series, then your 1.8 becomes the critical voltage. And if you have only single battery, what we call button cell, आपने देखा होगा ना, तो button cell का voltage सिर्फ 1.5 volt होता है. So in that case, the smaller instrument use this logic. 1.2 volt मतलब उनका logic high and 0 is उनका logic low. If you have two batteries जो आपके AAA सेल रिमोट में जाते हैं, तो उस केस में आपका 1.8 वोल्ट ये क्रिटिकल वोल्टेज होता है. उससे नीचे जो सिग्नल है वो लॉजिक 0 और 1.8 एंड अबव is logic 1. So remember these three numbers: 1.2, 1.8, and 2.2. Okay, typically 5 volt is always logic 1, and there are some logics levels where 9 volt is logic 1. Then you will learn as a mechanical engineer PLC SCADA system जहाँ पे 24 volt is logic 1. There are some systems where 48 volts is logic 1, and there are possibility of getting shock after 60 volts, and that's why you will never see digital systems operating on 60 volts and above. Typically they have a relay driver connected to the digital systems, and even 5 volt is sufficient to drive a relay. Next is reset pin. So reset pin is again make your output low, and it will override all the other inputs because it is actually hampering the flip-flop output directly. And that's why irrespective of whatever is there at pin number 2 or pin number 6, the actual flip-flop reset is gonna control everything. It's like a master. So it overpowers everything, whatever you have done earlier. Yeah, इस stage में जो भी हुआ है, it just overrides that. Then pin 5 is a control voltage. We have already seen it can override your 2/3 VCC condition and it will stop functioning. Typically, if you are not using this pin, you have to ground it using a capacitor to eliminate all the electrical noises that might appear. Pin number 6 is threshold. When it is greater than 2/3 of VCC, the output goes active high, and it monitors the discharging and charging time of the capacitor because of the transistor connected at the output. Pin number 7 is actual discharge pin, which actually directly allowed to flow of the current, and it is used for the timing. So this is the main timing pin, what we can say. And pin number 8 is just a supply, and any supply between 4.5 volt to 15 volt is suitable for IC SE555, which is a Fairchild company, and there is another variant NE555. ये मेडिकल ग्रेड का एंड मिलिट्री ग्रेड का 555 आईसी है. तो इन दोनों में डिफरेंस क्या होता है? योर रेगुलर 555 आईसी कैन लास्ट फ्रॉम -35 to positive of 80, 87, I guess. So typically very high temperature ranges it can handle, but military grade can work in -300 to +300 degrees. So आपकी टेम्परेचर रेंज अलग है, बाकी कोई चेंज नहीं होता मिलिट्री ग्रेड आईसी कंपोनेंट्स में एंड रूटीन आईसी कंपोनेंट्स में. तो ये मिलिट्री ग्रेड आईसी कंपोनेंट कब यूज करते हैं? इफ यू वांट टू पुट अ टाइमर इनसाइड अ वॉर टैंक, and if you are starting a war in the Antarctica like region, your electronics should not fail, and that's why it is very important to use military grade component in the applications where it's really cold, and there you want to work with some electronic part. Now there are three modes of operations of IC555. We will try to learn them one by one. Monostable, also called as one shot. Okay, so basically this IC will generate output once, that's it, and then it will wait for that. Okay, when the time goes off, it will again go to its stable state, and that's why it has only one stable state. So ये mono word जो है, that stands for one stable state. Then comes bistable state. Okay, this is kind of no memory to this. Whatever you say, he will do that. So when you say logic go high, it will go high and remain there. Whenever you say logic go low, it will go low and remain there. And remember, generally bistable capacitor cannot have any dynamic element. So there is no capacitor used in bistable mode. So where to use this kind of study? Because you are only telling to go high and you are only telling to go low. What is the use of this bistable? We will see later in the applications of 555. And then comes the most important mode of the IC555 called astable or free running mode, where it automatically generates this particular kind of waveform, and that is very funny. Without doing anything, it will start generating this. Even your Proteus shows this thing, and you will realize this kind of waveform can be only generated with the noise. So when you run this simulation, you will find that Proteus actually induces the noise from the air to the components so that components work properly as they will work outside the simulation in the real world. So that's why software Proteus is very powerful, because most of these models what we are using inside it as a IC, they are actually modeled so that it will work directly in the real time. So whatever you simulate, 99% chances that it will work directly when you do a proper simulation in the Proteus. And that's why we are teaching you this particular software for the course. Obviously ये लॉकडाउन की वजह से आप hands on नहीं कर पा रहे हो, and that is a very kind of big thing you are missing, because without handling electronics, only if you are very expert in Proteus, I am sure you cannot do anything. You have to touch the component at the end of the day. You might burn some breadboards, you might burn some wire, you might short IC555, you might blast IC741, but that experience is at the end of the day needed. So I hope we get a vaccine soon and you can handle some electronic components. In case that is not possible, whenever you come back to the college, I will recommend, I will be there in the college to help you, but I will recommend you go and touch this component, do it on your own, whatever you have simulated in the Proteus. Even with the controllers you make, you burn something, and then only you get that confidence. Even electronics engineer burns the component, so there is no issue if mechanical engineer also burns few things here and there. Next, now we will go into the details of monostable. I guess I still have time, so I will try to finish this particular topic. So monostable is like you generate a pulse for some time. As soon as this pulse goes below 1/3 of VCC, it will trigger the output to logic high. It will remain logic high for certain duration of the time. At that time, capacitor will charge and again cross 1/3 of VCC. The output will automatically go low. Now, one example of this is a simple circuit that you can keep it in your door of the cupboard. And what will happen as soon as you open this door, the light will fall from the outside to the inside circuitry, and then there will be a LDR which reduces the resistance and cause this voltage to go below 1/3 of VCC, and you can generate an alarm. I don't know if you have seen the first advertisement of Volkswagen when they launched in India. They give this kind of monostable multivibrator circuit in every newspaper, and as soon as you open the newspaper, this circuit starts to tell you information about Volkswagen, and uh, as soon as you close down the front page, it will stop playing that. So this is kind of application where monostable mode was used, and we will try to see the circuit diagram of monostable multivibrator. So yeah, we are going to make this circuit practically also in the lab, but just see here, we don't want to reset the IC. So always remember, whenever you are connecting IC 555, pin number 4 and 8 should always go until unless reset is required to the VCC. Now, since reset bar is written, so there is a NOT gate, and that's why when you pull this pin to VCC, actually you are not resetting the IC. Okay, so remember this thing, your pin 4 and 8 should short together and go to VCC. Now, next thing is your output pin, which you can connect anywhere, whatever is your output, maybe a LED or maybe a motor or maybe relay, anything you can connect to the output. Then we told that pin number 5 should not be left open. So you have to ground it using a 10 nanofarad capacitor. 0.001 microfarad is what we choose for this particular case. Pin number 1 is ground pin of the IC. So irrespective of whichever mode your IC is working in, you should always do these connections. Like by default, only some special case applications where these connections are not made in this way. But this is the basic connection for all three modes: astable, bistable, and monostable. Okay. Now, this particular circuit is for monostable. So it has a capacitor, it has a trigger pin, and then the capacitor is charged through a resistor R, and then it is connected to pin number 7 and pin number 6 threshold. So what will happen when you turn on the circuit? The capacitor will start charging. It will charge to value VCC, but while charging, as soon as it crosses 2/3 of VCC, what will happen is the capacitor will discharge through pin number 7, because as soon as threshold pin crosses 2/3 of VCC, the discharge pin gets shorted and the output will start falling. Okay, so we have to see the output will remain low because your threshold has already crossed 2/3 of VCC. Uh, when you give a pulse, which is a negative trigger, what is a negative trigger? Let me try to explain this with the help of a diagram. So a negative trigger. So generally when we say trigger, we give a pulse 0 volt to 5 volt. But IC 555 requires a negative trigger. Anything that goes below 1/3 of VCC to trigger the discharge capacitor connected at pin number 7. Also to take the output from logic low to logic 1. So this 1/3 of VCC level is here, and if you give a negative trigger, so by default, the voltage at this pin should be 5 volt. And as soon as you reduce this voltage to 0 volt, then it will put the output of your IC555 to logic high. As soon as that thing happens, your capacitor, which has already crossed 2/3 of VCC, will get discharged, and again it will start charging uh, to 2/3 of VCC. And if you find the total time for which the output remain high is given by uh, T equal to RC natural log of 3. There is a long derivation for this, so if we get time somewhere later in the course, I will tell you how this particular number comes. But for you, you just have to remember this value. Even someone can use a calculator and find the natural log of 3, and you can remember that value also. So the timing is, I guess, 1.1 RC for monostable multivibrator. So if I know my R is 1K and C is, let's say, 1 farad, then I can calculate my total time for which the output remains high. Just substitute the value of R and C and multiply it with 1.1 to get the final timing. Now, I will not start with bistable mode right now. I will stop recording. And if you have any doubts, you can ask me.